In the intricate landscape of technological innovation, few discoveries have the potential to fundamentally reimagine human sensory experience quite like the emerging field of spatial audio engineering. As we venture deeper into 2025, researchers at Penn State University have unveiled a technological marvel that promises to completely transform our understanding of acoustic communication, a breakthrough that challenges the very fundamental principles of how we perceive and interact with sound. This is not merely an incremental advancement, but a paradigm shift that traces its roots to decades of acoustic research, culminating in a moment that can only be described as acoustic alchemy. The journey begins with a simple yet profound question. What if sound could be as precisely controlled as light? The narrative unfolds in the laboratories of Penn State University, where an interdisciplinary team led by the visionary researcher Jia-Xin Zhong has been pushing the boundaries of acoustic science for nearly half a decade. Their groundbreaking research, comprehensively documented in the prestigious proceedings of the National Academy of Sciences, represents a quantum leap in audio technology. Historically, sound has been viewed as an uncontrollable, omnidirectional phenomenon. Acoustic waves naturally diffract, spread, and bleed into surrounding spaces, creating background noise and audio interference that seemed insurmountable. Traditional acoustic science accepted these limitations as immutable laws of physics, until now. At the heart of this revolutionary technology lies an ingenious manipulation of ultrasonic waves, sound frequencies that exist far beyond the threshold of human hearing. The researchers engineered two ultrasonic carrier waves with remarkable precision, one at 40,000 Hz and another at 39,500 Hz. Through a complex process of nonlinear acoustic demodulation, these waves generate a new sound wave at exactly 500 Hz, a frequency perfectly aligned with human auditory perception. The mathematical complexity behind this breakthrough is staggering. Researchers developed sophisticated equations that describe the intricate dance of sound waves, including a critical formula that relates the refracted sound wave angle to the phase gradient along the metasurface. This isn't just theory, it's a carefully engineered solution that transforms the very nature of acoustic propagation. Acoustic metasurfaces represent the physical embodiment of this technological breakthrough. These are not theoretical constructs, but precisely 3D-printed engineered surfaces capable of manipulating sound waves with unprecedented accuracy. Each metasurface is a marvel of microengineering designed to bend, focus, and redirect sound waves with the same precision that optical lenses manipulate light. The manufacturing process involves intricate techniques like kirigami-based reconfigurable designs, where microscopic geometric transformations allow dynamic beam steering. Metallic microstructures can rotate and stretch, creating sound beams that can flip or split with sub-millimeter precision. In validation tests, these metasurfaces demonstrated remarkable capabilities, with neural network-assisted models achieving less than 1 decibel error in localized control ranges. The potential applications of this technology extend far beyond mere acoustic novelty. In public transportation systems, for instance, the technology promises to revolutionize accessibility and communication. Drawing from UITP, International Association of Public Transport Guidelines, these acoustic metasurfaces could transform electric vehicle alert systems by creating low-level, non-intrusive sounds that alert pedestrians and visually impaired users without disrupting quiet zones. Imagine smart devices providing spatial audio cues about approaching vehicles, enhancing situational awareness while maintaining environmental tranquility. In medical settings, hospitals could communicate sensitive instructions discreetly. Museums could deliver personalized exhibit descriptions to individual visitors without disturbing others. The technology even holds promise for neuromodulation, with binary acoustic metasurfaces, BAMs, capable of non-invasively correcting skull-induced beam aberration. Unlike traditional headphones that require direct ear contact and isolate users from their environment, acoustic metasurface technology offers a fundamentally different approach to sound delivery. Where headphones create barriers, this technology creates bridges, delivering sound with zero physical contact, preserving environmental awareness, and eliminating issues like listening fatigue or skin irritation. Validation studies using simulated head and torso dummies have demonstrated extraordinary precision. Metasurface sensor arrays achieved 98% accuracy in object detection and localization, with the ability to separate sound sources with 97% accuracy in controlled environments. The research team has been meticulous in addressing potential safety concerns. The system must comply with stringent FDA guidelines, maintaining a safety margin of 1 to 5,200 for ultrasound exposure. This involves precise control of beam intensities, continuous monitoring of thermal and mechanical indices, and preventing potential biological effects. Moreover, the technology aligns with critical regulatory frameworks like the Persons with Disabilities Act of 2008, ensuring inclusive design principles are at the forefront of development. Implementing this technology isn't just an acoustic engineering challenge, it's a computational complexity problem. Researchers are exploring hybrid approaches that combine traditional beamforming methods with advanced artificial intelligence. Techniques like long-short-term memory, LSTM. Neural networks can predict and adjust beam parameters in real time, learning from environmental data and minimizing interference. In the profound words of lead researcher Jia-Xin Zhong, they've created a world where someone within an audible enclave can hear something meant only for them, enabling sound and quiet zones that were previously unimaginable. This isn't just the end of headphones, it's the beginning of a world where sound respects boundaries, where acoustic experiences are personal, immersive, and fundamentally respectful of individual space. The future of sound is not about volume, it's about precision. Revolutionize your understanding of science, subscribe, like, and comment to join us on the frontiers of discovery.